Hi guys. So this is the probably fifth time I've tried to record this video. Cross your fingers, hopefully it works. So today in class we're going to be practicing what I would like you to be able to do outside of class. When I looked at all of the material that we had to cover before the AP exam, it's a lot. And there's a reason that last year they didn't cover it all, which there's no way to go over all of it, but we want to make sure we're as prepared as possible. And the things that we don't cover, they're not super present on the test. There are some things that, there's more questions on certain content areas. Our goal is we're going to start doing a flipped classroom, which basically means you'll watch the video outside of class. You'll come in, we'll ask questions, we will talk about it, understand it much more deeply, and then we'll do the same thing. We tried that, but the videos that were provided to me were 40 minutes, 50 minutes. That's ridiculous. The goal is to make something that is 15 minutes, maybe a little bit longer, that you can watch in one sitting at breakfast if you really need to, something like that. And then when you come to class, we can just address questions. We don't have to go through it slide for slide. That also means that you might be pausing this video to take notes. You might rewind it a little bit, but it shouldn't take an hour, 2 hours to go through it all, and we don't have to do it in class, which is no fun for me and no fun for you guys either. So this video will probably last about 15 minutes. The past 5 times I've done it, I have had to stop a little bit short and then make a second video that's a tiny bit longer. So probably in total it'll be 20 minutes. You'll have to switch over to the next video when this one stops, but it should be easy, I hope. This is my first time using it. Well, my first time trying to use it correctly, so hopefully it works. And in class on Monday, which is right now, we're going to do all of it together so that when you are doing it on your own at home, you feel more comfortable doing this. This unit, the biochemistry unit, we're just finishing up the endocrine system, and that's the end of the body systems that you need to know, or at least need to review from general biology. Technically in Massachusetts, you do go over some anatomy in Gen Bio if you had time to. But biochemistry is mostly just chemistry review with a biology spin. So I'm going to go through this pretty quickly. If you have questions, write them down. If you need to pause them and write down definitions, do that. But I would just make sure you write down or hit upon those important terms that you don't remember. A lot of these, hopefully, if you were successful in chemistry and you had Miss Wilson, who has a great curriculum, you should feel pretty confident with these terms. So things that you need to know. Element, pure substance, can be broken down. There's 92 naturally occurring ones, but with the biology flip on things, we know that there's only, I think, 9 elements. It comes up later. There's only a couple of the elements that we see in like the living world. The other term you should know is compound. 2 or more different elements combined in a fixed ratio. So sodium chloride, H2O, CH4, things like that. The only other term that's not in here is molecule, which would be 2 of the same elements bonded together. So H2, hydrogen actually never exists. Hi! Guys, look! Anyway, H2 always exists on its own, so, or in a pair, so that's going to be still considered a pure substance. Like I was mentioning before, out of those 92 elements, only about 20 to 25 are essential for life, and out of those 20%, only carbon, hydrogen, and oxygen, a little bit of nitrogen, make up the majority of living matter. So everything in our natural world, everything in biology is mostly carbon, hydrogen, oxygen, and nitrogen. So they have a whole study on organic chemistry, which is mostly carbon and oxygen compounds. Again, this table just shows what your body is made up of element-wise. We're mostly oxygen, carbon, and hydrogen. Makes sense because we're made up of a lot of water. and then a lot of carbon, a little bit of nitrogen. In the air, actually, there's a lot of nitrogen. We need to know the structure of the atom. I think this is really review for you guys. The idea that the nucleus is protons and neutrons, and it's positively charged in there, and the electrons are moving around that nucleus, and they are a negative charge. And we'll talk more about their properties. When we talk about electrons, we just need to be careful that we don't fall back on the simple form that you learn in chemistry, which is orbitals or rings or things like that, because electrons actually don't move in a pattern like that. They exist in a cloud and they kind of bounce around, and we could guess that they're kind of in that space, but there's actually a 5% chance that they're not even in that cloud, now that they've done research on the electron cloud versus the electron orbital and ring diagram. Other terms that you need to know, atomic number is the number of protons, therefore usually the number of neutrons unless it's an isotope. Also, normally, unless we're an ion, we have the same number of protons, neutrons, and electrons. So carbon has 4 protons, 4 neutrons, 4 electrons. It gives it a net charge of 0 because we've got 4 positives, 4 negatives, and then the 4 neutral atom or subatomic particles. The other thing you need to know is atomic mass. When I taught chemistry, I only talked about atomic mass because mass number is specific to that atom. And then, so for each atom, let's say of carbon, it's going to have slightly different weight. The atomic mass is the average weight of a carbon atom, which is more relevant to what we're talking about. Speaking of the weights of things and isotopes, isotopes are going to be when we have extra neutrons. This is most important in carbon dating because there's a couple different versions of carbon. All of them are still neutral, just different amounts of neutrons, and they decay. So if we can look at how much a thing that was living, how much carbon that thing that was living had when it died and what it has now, we can look at exactly how old it is. The only other one that you might need to know that's not in the slides is ions, which is a change in the number of electrons, which is going to make it charged positively or negatively. And so obviously that doesn't change the weight because electrons really don't contribute to the weight of an atom. When we talk about electrons, we want to steer clear of talking about like the shell or a ring or an orbital and talk about clouds, because electrons bounce around within a space, sort of, not really. What we do know is that because they're moving, they have energy, and they have potential energy because they are pulled into the center. They're never going to leave the atom, unless you're like dividing the atom, which would be causing explosions. And so basically, the further away they get from the nucleus, the more energy they have. This is why when we talk about 1s, 2s, 2p orbitals, the higher the number, or the further away the electron, the more energy it's considered to have because it has more freedom to move because it's not being pulled as much by the nucleus. The closer it is, the less energy it's considered to have. The other reason, besides distance, that allows the electron that's furthest away to have energy is that there's all sorts of stuff in between the nucleus and that furthest electron. So if you look at the diagram, you've got your nucleus, you've got your third shell or third cloud. There might be a couple electrons that are acting as a shield to that final electron, and so it won't be pulled in as close, and so it has the capacity to have more potential energy. Why are electrons so important? That dictates how they behave because it dictates how they bond. If I have 8 electrons, 8 valence electrons, I won't bond at all. I don't really have a lot of chemical reactions or interactions because I'm happy just hanging out. If I have 7, I'm trying to get that last one, I'm very reactive. And so in the natural world, in biology, bonding and what happens when elements interact totally is the point of talking about chemistry in relation to biology. Again, we want to move away from thinking about rings, but when we talk about valence electrons, we kind of think about like, oh, we have that final ring that needs 8. Think about it as like the cloud that needs 8. That cloud holds your valence electrons, and valence electrons determines what you do because those are your bonding electrons. If I have 8 and I'm a noble gas, I don't bond with anything else because I have those 8 already. If I'm fluorine, chlorine, things like that that have 7, I'm very electron hungry because I'm 1 away from filling that shell, and so I am very reactive. That's why I believe if you do chlorine and like or solid chloride and water, you'll create an explosion. It's highly reactive. Something like that. I don't know. Remind me what it is. So again, as we move through thinking about chemistry, we just want to avoid talking about the shell model because the shell model doesn't help us think about the 3 types of bonds, which you should know. Instead, we should think about the orbital diagram that has a different cloud. Basically, the letter indicates what shape it is. S is spherical, P is dumbbell, D is going to be a clover shape. And the idea is that the electrons in that, so 1s, lowest energy level is 1, and S is the sphere, has 2 electrons, right? If you, one spinning up, one spinning down. But really, they're just bouncing around in that space somewhere. And there's a 5 to 10% chance it's not even, those electrons aren't even in that space. The same goes for the p orbitals. There's a 5 to 10% chance that those electrons are totally somewhere else. And so it's really not a ring anymore that we talk about when we talk about electrons. Again, the number indicates the energy level. Higher energy level, higher energy level is going to be further away. The letter indicates the shape, the general shape. The last thing I'm going to talk about before you pause this video and you switch over to the last couple slides is making sure we know the 3 different types of chemical bonds, covalent, polar covalent, and ionic. Obviously, covalent, they are sharing. This is usually 2 of the same elements. Polar covalent, they're shared unequally, and then ionic, it's going to involve a transfer, which creates 2 ions, and the negative charges are attracted. I'm going to pause this video here. You'll need to switch over to the part 2 of this PowerPoint. There are only a few slides left, and so I should be able to wrap things up really quickly, and hopefully this feels like a review already.